Welcome. Today we will talk about interactive feature engineering for supervised learning with our new tool Dataset Evolver. So, what is feature engineering? It is the task of altering feature space for a given learning problem with the objective of improving model accuracy. It is performed by constructing new features from the given ones through the use of transformations, which could be mathematical or statistical functions, and also removing certain unwanted features. Feature engineering is largely performed manually. It relies heavily on a data scientist performing a long process of trial and error, which is guided by intuition and sometimes domain expertise. The process actually takes quite a bit of time because of its nature of trial and error, and is also prone to bias and error because of the human dependence. In this demonstration, we highlight two of our novel algorithms that perform feature engineering automatically. These algorithms have been implemented as a part of an interactive Jupyter notebook where they can be used by a data scientist to assist with the task of feature engineering. This means that the data scientist can go about doing the regular order of modeling with the availability of these suggestions from the new algorithms. This constitutes a mixed initiative system which can help perform feature engineering more effectively as well as more efficiently. The first algorithm is called LFE, or Learning-Based Feature Engineering. It learns correlations between feature distributions, target distributions, and transformations over thousands of data sets in the past and uses those patterns to predict effective feature engineering choices for any new given dataset. Secondly, Cognito provides a performance-guided exploration of the feature engineering choices, much like a manual trial and error strategy, however automated. It learns its exploration strategy through reinforcement learning over historical datasets as well. Let us take a brief look at the dataset evolver. For example, here we have loaded a classification dataset into a Python Jupyter notebook. Let us see what this dataset looks like. So you can see here that there are 27 columns, which means 26 features and a target. And this is a classification problem with 0 and 1 classes. As you can see, all the features are numerical. However, there's no real description provided for the features themselves. This makes it hard for a data scientist to prioritize which feature transformations to apply. So let's try some automated feature engineering. We have now asked the dataset evolver to have a look at the dataset and suggest some feature engineering choices. Once the initialization is done, we first perform some linear exploration using LFE. By using this command, we can visually browse different options suggested by LFE. For instance, you can see here on the left that an original feature called the predictor one had two classes with quite a bit of overlap. This is essentially a scatter plot. And on the right, you can see when a frequency transform is applied to the predictor one feature, you can more clearly see the distinction between the 0 class and the 1 class. We can keep on doing this until LFE runs out of recommendations. So you can see another feature here, again with frequency transform, predictor 3. There's a visual evidence of better separation between the two classes, and hence uh, we can assume that adding this feature is going to perhaps improve the accuracy of the model. Upon looking at several such recommendations from LFE, we are now ready to include those suggestions as a part of our model building. I'm preparing a list of the features I particularly liked. Using this list, now I'm going to add the new features to the base data set. As you can see here, the new columns were added to the base data frame. Now using a compare function, we can actually test the accuracies of the previous data set and the new data set. It should be noted that we are doing a 70-30 split between the training and the test data sets, and it's happening implicitly here, so it cannot be seen. But you could use cross validation as well if that is a more suitable choice. So we can see here that for the original data set, the average F score is 0.89. However, if we add these specific features, the average score improves slightly to 0.9. In addition to adding the new features manually, we can also let LFE decide which is the best combination of features to add by using the auto add features method of the Explorer. Now let's see what is the performance of this dataset. So as you can see that the original data set's F score was 0.89, and the one in which we picked and chose few new features, the score was zero point 0.9, and in the auto suggest one, the score is even better, 0.92, which shows the effectiveness of LFE's feature generation. Now, in order to perform a deeper hierarchical exploration of feature engineering options using the second algorithm, we can call the same explore method, but with the tree mode. Here, you can see a hierarchical exploration through different transformation options. This is a highly interactive user interface where you can specify the metric, different models, and so on. In this demonstration, we also propose to show how the two techniques, the exploration-based and the learning-based, work together in a positive feedback loop, providing useful feedback to each other and improving the feature engineering result to an even better degree. Thank you.